All right, let's go ahead and calculate the energy released in a very important nuclear reaction known as the triple alpha process. So the triple alpha process, as the name suggests, is when we take 3 alpha particles and combine them to make carbon 12. So this is the triple alpha process. And we want to calculate the energy that's liberated in this. This is a fusion reaction because we're taking helium atoms and we're fusing them together to make carbon. That's a bigger atom than helium, right? If we look at the periodic table. So we need to first start with a balanced nuclear reaction. You may recall that an alpha particle is a helium nucleus. And so its nuclide symbol is this. It has 4 total nucleons, and 2 of them are positively charged. Right? So there's 2 protons and 2 neutrons. Triple alpha means we need a coefficient of 3 in front. So if we have 3 of these nuclides that are going to all crash together and give us 1 carbon 12, which has 6 protons. And that's it. I mean, that's the reaction. 3 of these smash together, give us 1 of those. Balance, right? If you crunch the numbers, 2, 4, 6, yep. 4, 8, 12, yep. Right, they're all there. All right. I think it's also helpful to sort of see this with like a physical model, or you don't have to build it, but like you can visualize like what is a helium nucleus? It's something with 2 protons and 2 neutrons. Like there's a helium. We got another one. We got another one. So 3 helium nuclei, and this is why the reaction was thought to be sort of, this can't work. What are the chances we can get all 3 of them to crash together, and stick together to give us this? Like we need 3 of these, so how else would it go? Can you think of a better way to get carbon? So it's like you have 3, and again, it's be really, really hot. So like the inside of a star is hot enough that there's enough kinetic energy. These things are bouncing around or moving with a lot of energy, and they collide. If they get close enough, that they can actually stay bound via the strong nuclear force. It's like what keeps the nucleus of an atom together? Like why don't these positive charges just repel and sort of everything flies apart? Because there's a nuclear force that is stronger than the electrostatic repulsion of like the charges that make up the protons. But remember, it acts over a very short range. And so carbon is a very stable atom. But that doesn't mean that these reactions are easy to make work. Just because carbon is stable doesn't mean that we're here fusing helium atoms into it. Stars can do it. Stars have the necessary heat and pressure. Pressure is like how much force per area. So at high densities, where there's lots of matter and all that matter is very hot, that's kind of the ingredients we need for nuclear fusion. High densities, high temperatures, just like inside of stars and the early universe. And so these 3 sort of alpha particles just 6 positives, 1, 2, 3, 4, 5, 6 neutrons. There you go. Like they all fuse together and you give us 1 of these. And maybe there's going to be some energy release. In fact, we know there is, right? Because this is higher up on that binding energy per nucleon than helium is. Okay, so there's more, like each one of these nucleons has more binding energy in it, okay, as per that graph, than any one of these. Okay, there's binding energy in these, like these have binding energy to keep them bound, but there's more binding energy per nucleon here, which means this is more stable than these. Okay. Now let's look at the data that was sort of suggested to us. The mass of a helium nucleus. So we're given the mass of a helium nucleus is equal to 4 point, and we have to have this very precisely, 001506. And then lowercase u is the unified atomic mass unit. I think one of the pieces of information you may have just jotted down if you were copying down the question as I presented a moment ago, 1.66 by 10 to the negative 27 kilograms. We're going to have to turn atomic mass units into kilograms as we plug it into Einstein's famous mass energy equivalence equation. The mass of our carbon is equal to 12.000000 U. And so this is kind of, interesting because we actually define the weights on the periodic table with everything being relative to carbon being exactly 12. Like it's not a coincidence that this number is so precise. it's sort of, we chose carbon 12 to be exactly 12, and everything is relative to that. So hydrogen, for example, has a mass about 1/12 that of carbon. But we define this in Avogadro's constant. So Avogadro's constant is like a mole, how many things are in a mole. If you remember from chemistry, there are 6.022 by 10 to the 23 things per mole. And so we define this as there's exactly 6.022 by 10 to the 23 carbon atoms in 12 grams of carbon 12. And then that gives us a way to sort of turn atomic masses on the periodic table into like grams per mole, into molar mass. As a chemist in a laboratory, I can weigh out grams of reactant, grams, I can measure grams of product, but I can't really, say I need 3 heliums, here in my lab. It's like I've got a sample of helium gas that's billions upon trillions of these, right? So I need this idea of the mole to sort of bridge me from my macroscopic sort of laboratory to the submicroscopic realm that the reactions are actually occurring within. And Avogadro is a brilliant, scientist that came up with, his value, Avogadro's constant. So, this is exactly 12 for a reason. It's like not a coincidence. So everything is based on carbon being exactly 12. Rather than saying like defining a hydrogen to be exactly 1, and then this would be like, a little bit different. It's easier to measure sort of this carbon 12. So they define everything based on that. All right, so this is what we've got. And then we've got here. So all we got to do is triple this, right? Because we have 3 of them. So we're saying each one of these has a mass of 4.001506 unified atomic mass units. But I've got 3 of them, right? So like what's 3 times this number? If you just kind of look, if we multiply something that's a little bit bigger than 4 by 3, we're getting an answer that's a little bit bigger than 12, right? So there's going to be more mass here than there is here, which means if there's a mass defect, a change in mass, that has to show up as energy according to E equals mc squared. So because the 3 heliums are going to be more massive than the 1 carbon, I have to like add in the extra energy, right, equal to the change in mass times the speed of light squared to make it balanced. So it's like nucleon number is conserved, atomic number is conserved, and mass energy are conserved, right? Mass and energy are sort of one quantity, hyphenated, not the mass, not the energy, the mass hyphen energy is conserved. So because there is a deficit in mass, a mass defect, it must show up as energy. That's what we're calculating now. So what's 3 times this? Here I will use a standard algorithm of multiplication. 6 times 3 is 18. The 1, 5, 1, 4, 0, 0, 12, right? 12.004518. Do I line that all up good? Good enough. All right, and so we want the difference, right? So I kind of just wrote it like this. It's easier for me to do my standard algorithm of subtraction now. 8 minus 0 is 8. 1 minus 0 is 1. 5 minus 0 is, I'll get my calculator. Oh wait, that joke's not funny anymore. You know who I'm talking. You know who I'm talking to. Okay, I was watching. 0.004518. U, and each U is this many kilograms. So I think you can anticipate the next step. Let's see, mental math. 1.66 by 10 to the negative 27. Let me pull that up in my brain. 1.66 by 10 raised to the negative 27. Okay, I got that number in my brain now. I'm going to multiply it by, how would we read this number here? This is like tens, hundreds, thousands, 10,000s, 100,000s, millions. So this number is 4,518 millions. So multiply 4,518 millions by 1.66 by 10 to the negative 27. And, try to do it, in your head. Use a little bit of mental math like I am this week, or this afternoon. So I get 7.49988 by 10 to the negative 30 or about. I think that's right. Check that out your own mental math. Yeah, check it out. This times this is this. That's how much mass. That's the difference in mass. Okay, if you look at step 1 over on the other chalkboard, it says Balance the nuclear reaction by ensuring nucleon number and proton number are conserved. Check, we do that over there. And then it says, because mass energy is conserved, the change in mass is equal to energy via equals mc squared. So calculate the change in mass and then convert it to energy. So we're at the part where we calculated the change in mass. Now we got to convert it to energy. So energy is equal to this mass times the c light squared. And for the purposes of our quizzes, you can use 300 million meters per second for C, or you could use the more precisely known value, 299,792,458 meters per second. Your answers will be close enough that it won't really matter. So the mass is this, 7.49988 by 10 to the negative 30 kilos times 300 million meters per second squared. A kilogram meters squared per second squared is a joule of energy. Don't forget that we can convert joules to electron volts by dividing by 1.6 by 10 to the negative 19 joules per electron volt. Remember, electron volt is the energy that an electron gains as it travels through a potential difference of 1 volt. And electron volts to mega electron volts are 10 to the 6 electron volts per 1 mega electron volt. So once we get sort of this answer here in joules, we're going to want to divide it by this and then divide it by 1,000,000 to get our answer in mega electron volts. Okay. So this one here gives me 6.749892 by 10 to the minus 13 joules. And so you kind of think about, like, if you just got this answer, it's a 10 to the negative 13. What a small number. Isn't there a better unit than joules to measure this? Like, joule is too big of an energy unit. We need something like, oh yeah, electron volt. That's the small one. So like if you're measuring tiny energies, electron volts. You say, wait, tiny energies, you're telling us this is like very energetic. This is nuclear fusion. You're saying there's tiny energies. Remember, for every 3 helium nuclei that make 1 carbon, yes, this tiny amount of energy is liberated. But we could say, well, how many of these, helium atoms would be doing this to carbon inside of like a star? And again, that's when you're going to multiply it by Avogadro's number, 10 to the 23. Like we're going to have a huge sample of these atoms. It's not just going to be 3 of them or 6 of them. It's going to happen twice. We'll make 2 carbon atoms. We make enough to fill a planet like Earth with carbon. Okay, so like these reactions occur in stars, and then when they go supernova, they flood the universe full of carbon, so that planets, rocky planets can then form. All right, so like Earth is old enough that the universe has already done this enough so that there's a lot of carbon on this planet, including in our bodies. Right, we're carbon based. So we look at this number and we'd say, well, that's too low. Let me convert it to electron volts, and so I divide it by 1.6 by 10 to the negative 19, and that gives me a really big number, 4218688.2.5. So now we're in electron volts, and we say, well, that's maybe better than 10 to the minus 13. Imagine writing out 0.000, 12 zeros before you get to 6. So this is okay, we're only like 6 orders of magnitude, but that's when you say, okay, I could rewrite this then as, since I have 1, 2, 3, 4, 5, 6 places after this, first digit, I could rewrite it as 4.22, we'll say, we'll round to the 3 significant digits, times 10 to the 1, 2, 3, 4, 5, 6 places, right? If I move the decimal point from here to here, and I moved it 6 places, and so that's sort of the rule for scientific notation. So it's 4.22 by 10 to the 6 electron volts, and 10 to the 6 million, okay, capital M for mega. So a mega electron volt, 4.22. So it's equivalent to like once I've done this division, I'm in electron volts, well, I have to divide by another million. So it's like saying, okay, if I took this number and divided by 1,000,000, it would become this, right? So it's like the way to write this is here, or you could just think about it like this. This prefix m means 10 to the 6. So I could literally convert it by just writing it like that. So it's like 4.22 by 10 to the 6 electron volts. Same thing as 4.22 mega electron volts. Mega means 10 to the 6. And I hope that you'll agree, this is more of like an opinion thing, but I think that's the cleanest way to report the answer. I like this better than like 10 to the 6. I like it better than 10 to the negative 13 joules. It's like, if you said how much energy is released in the triple alpha process. Triple alpha process, double hyphen, how much energy released when stars do this? I like the answer 4.22 mega electron volts. Okay, it's better than like 6.749892 by 10 to the negative 13 joules. So it's that many mega electron volts. And again, per reaction. Okay. So a lot of these reactions occur. So like the next logical sort of step in a calculation like this might be to multiply this by like Avogadro's number. Say, what if 1 mole of helium reacted? And then we have sort of an idea about, like a mole of helium weighs what? 4 grams. So if I have 4 grams of helium in like a balloon, okay, I have a mole of that helium. I let all, the entire mole react, give me a mole of, carbon, which would weigh exactly 12 grams, right? So imagine like 12 grams, it's like 28 grams in an ounce, so like, a little bit less than half an ounce. So imagine taking a pencil which has graphite, like carbon, okay, in your pencil lead, it's not really lead, it's graphite, right? The allotrope of carbon. And you just like shaved your pencil onto a triple beam balance until the scale went up to 12 grams. You're like, okay, I got 12 grams of carbon 12. Let's assume it's all carbon 12. Then you know that in that 12-gram sample of carbon 12, you've got 6.022 by 10 to the 23 atoms. A huge number of atoms in that little 12-gram pile. So remember that the sort of how low these numbers are an artifact of we're simply examining a single reaction, but these reactions are going to occur. I mean, trillion doesn't even do it justice. Quadrillion, quintillion, hexillion. Huge numbers of these, carbon atoms are going to be created inside of stars, right? So this is how we're liberating a tremendous amount of energy inside of stars. That not just this fusion, but like even the fusion that the sun is doing right now, hydrogen to this, the helium, is releasing a tremendous amount of energy from that fusion. Because again, the binding energy per nucleon for helium is a lot higher than it is for like deuterium, which are the paths that lead to this. And we're thankful for that because if you look through the window, there's like sunlight coming through the window. And that's the sort of the byproduct of this. Remember, is that this energy shows up as what? Kinetic energy. Okay, so if it's like fission, then the fragments, okay, can have some kinetic energy, like when a heavy element fissions, it splits apart, and those things are going to have kinetic energy. But also gamma photons. Gamma photons are always sort of created too. And so like the light that we see from the sun is an artifact of these nuclear reactions that the sun is sort of doing. All right, and so that's how we calculate the energy released in a fusion reaction. If you get a fission reaction tomorrow for your quiz, hopefully you'll be able to sort of translate this thinking into that, okay? So you've got really the remainder of the period now, about 50 minutes left in class. Go ahead and cut YouTube loose, okay? See you later, YouTube. We'll see you next time.